Okay, so now in the final stage, okay, we come to the final stage. We have done the glycolysis, we have done the link reactions, okay, and we have this Krebs cycle. So done for these 3 stages already. Now we come to the final stage of the aerobic respirations, which is oxidative phosphorylations, where we are going to use the energy, okay, for the phosphorylation ADP. ADP comes from the activity of the electron transport chain, okay. And where do this take place? Inner membranes of the mitochondria can do this for us. Okay, so look at this diagram now. Okay, what actually happens here? Now, previously in the few lessons back, we do learn about this oxidative phosphorylation, where we accumulate a lot of the hydrogen atoms. Correct or not? Okay, so hydrogen ions, the protons here, we accumulate a lot of protons in the intermembrane space, and matrix have low concentration of protons. Therefore, we have a steep proton gradient or steep electrochemical gradient. So for proton want to move back from the intermembrane space back to the mitochondrial matrix only one way. They have to go through this ion channel, which associated with the ATP synthase. So this ATP synthase is going to catalyze the reactions of the ADP together with the phosphates from ATP. And we already learned about this binding change mechanism, right? Binding change mechanism, correct or not? Okay, so when this proton move, okay, when proton move from the intermembrane space back to the matrix, okay, intermembrane space back to the matrix, so energy release, because high potential energy, low potential energy. So therefore, when they move past this ion channel, energy is released. So this energy is used to phosphorylate the ADP to form ATP. So what we learn actually is a chemiosmosis. So some students actually ask me, what has been chemiosmosis? Now, osmosis, we have learned this before, right? Osmosis means that's the passive movement, okay, of the water molecule from high water potential to low water potential, correct? Okay, across this phospholipids, so across this selectively permeable membrane, selectively permeable membrane. So, but in this case, it's something similar to osmosis, because why? High potential energy, low potential energy. So that's why energy is released from high to low. But in this case, not water anymore. It's not water molecule anymore. It's the proton. So therefore, we deem it as chemi. Chemi means chemical. Osmosis means down potential gradient. Are you clear? Osmosis is the movement down the potential gradient. But we haven't looked at this, how we can accumulate the protons in the intermembrane space, how we can accumulate. So now we have to look at this electron transport chain. So in fact, oxidative phosphorylation consists of 2 parts. It consists of 2 parts. The first part is electron transport chain. Second part actually is chemiosmosis. So what actually happens in this electron transport chain? So at the inner mitochondrial membrane, you can see that we do have this, what we call the electron carrier. The purple color protein here is termed as the electron carrier. So a series of electron carrier form a chain, in this case, form a chain which termed as electron transport chain. So when you describe this, you say that a series of electron carrier, correct? And you say electron transport chain, correct. But you cannot say that a series of electron transport chain, because it's once, only one, not many series, okay? Only one electron transport chain, not a series of electron transport chain, but we can use the term a series of electron carrier. So what this electron carrier will do, okay? Then it depends on the reduced NAD and reduced FAD. So the first process take place here is our reduced NAD. What they're going to do here, they're going to regenerate back. So it means that initially they carry the hydrogen atom, so now they release the hydrogen atom. And we do know that hydrogen atom is not stable. Immediately, this hydrogen atom dissociate into a proton hydrogen atom. Okay, this hydrogen atom dissociate into the protons and electrons. Okay, dissociate into the proton and electrons. Okay, so now these 2 items, they have their own fates here. Okay, this electron, what happened to this electron? I purposely use a red color here because these electrons, because we kick the electron out of the shells, correct? Hydrogen atom, you need to kick out the electron. So it means that they have high energy level. So when they have high energy level, they will be carried along this electron carrier. So can you see that? The yellow color means the flow of the electron. Can you see that? Electron are passed from one electron carrier to another electron carrier to another electron carrier until at the end, the last electron carrier. Can you see that? The electron. How about the proton? Proton will remain in the matrix until this electron pass through the electron carrier, and they have high energy, too high this energy. We want to release the energy. So this electron, when they pass through, when this electron pass through the electron carrier, what happened to this? The energy of the electron now released. Are you clear? You try to imagine, okay? So if I ask you, a person, to carry a very hot thing, you try to imagine, one person carry a very hot thing, you say, oh, very pain, very hot, right? But if I ask you to pass along, so try to imagine, this process, how I draw it. Okay, try to imagine. Okay, you alone carry a hot item, okay, very hot item, and ask you to transfer them to a destination here. One person, very hot. Can I see that? But what we're going to do here is, we have many of them. Okay, you ask your friend. So one person to pass, another person to pass. So it's very hot, but it's just immediately, just one, a very quick one. You pass it to another person, you pass it to another person. So during you pass this electron, the electron actually releases energy. So this energy will be used to pump the proton from the matrix to the mitochondrial intermembrane space. Are you clear? So it means the electron, can I see that? Electron pass through the electron carrier. So hydrogen ions will be pumped from the matrix to the intermembrane space. Continue. Therefore, we accumulate high concentrations of protons. Now we accumulate high concentrations of protons at the intermembrane space compared to the matrix. Are you clear? Clear? So again, guys, first event, reduce energy, now release hydrogen atom. This hydrogen atom dissociate into the protons and electron. And this electron will be passed or transferred along this electron carrier or along the electron transport chain. So during the process of transfer, energy is released. Therefore, this energy is used to pump the proton from the mitochondrial matrix to the intermembrane space. Therefore, there is an accumulation of the protons at the intermembrane space. Okay, so for protons to diffuse back to the matrix, they cannot pass through the phospholipid bilayer. Okay, this inner mitochondrial membrane, impossible. So for them to come back from the intermembrane space back to the matrix, they have to go through the proton channel, which associated with the ATP synthase. Are you clear? So when associated ATP synthase, therefore the energy released by the proton will be used to phosphorylate the ADP to form ATP. So we have two parts, electron transport change and also chemiosmosis form the oxidative phosphorylation. Okay, now the question here is, the proton move up and down, and then we have accumulation of proton here. Definitely is a dangerous, because proton, they are acidic, cannot. Okay, so what we're going to do here is we need to have the oxygens here. Can I see that? So what is the function of oxygen? O2 now will act as final electron acceptor. Okay, final electrons acceptor, at least you say this, or final electron and proton acceptor. So what they do? So you can see that this water molecule, I said, it will be formed because of O2 will take the hydrogen ions together with the electrons to form H2O. Are you clear? Now it's not equal. Full equation. So a full equation will be O2 plus 4 electrons. Okay, to get one, right? Get two molecule of water. This is the balance equation. Okay, so in fact, what will happen here is your protons together with electron forming the hydrogen atom. This hydrogen atom will be accepted by oxygen and forming water molecules. So it means that oxygen is reduced, okay, to form water. Okay, so let us look at this. So both reduced NAD and reduced FAD are passed through the electron transport change at the inner membrane. So therefore, hydrogen atoms are removed from these two hydrogen carrier, split into the proton and electrons. So the energetics electron is transferred to the electron carrier. So as these electrons pass away, move from one carrier to another carrier, so means that energy will be released. So this energy is used to pump the proton from the matrix to the intermembrane space. Therefore, we set up this steep concentration gradients, or you can say steep electrochemical gradient. Okay, so proton will pass back or move back into the mitochondrial matrix through the protein channel or proton channel in the membrane space, moving down their concentration gradient or electrochemical gradient. Okay. So associated with each channel, okay, associated with each channel is the enzyme ATP synthase. So therefore, as the proton passes through the channel, the electrical potential energy or potential energy is used to synthesize the ATP in the process of chemiosmosis. How about oxygen? Oxygen acts as a final electron acceptor. So in the mitochondrial matrix, electron and protons, can you see that, combine together? Electron and proton combine together and reduce the oxygens to form water. Okay, you can write down the equations here. So first, hydrogen ions and electron combine to form the hydrogen atom. So total 4 of them. So these 4 hydrogen atoms combine with the oxygens to form 2 molecules of water. Can you see that? If 4 hydrogen atoms combine with the oxygens here to form 2 molecules of water. Okay, so means that oxygens here, can you see that? We say that because they accept hydrogen atom. When they accept the hydrogen atom, so means that oxygen is reduced to water. Okay, we say that oxygen is reduced to water. Okay, so in average, so just now we have a student ask me how to get 28 ATP. We are going to calculate later. So average, the energy release here, because we know that the energy involved in release. So per reduced NAD, they can be used to synthesize 2.5 molecule of ATP. Per reduced FAD, the energy release will be able to synthesize an average of 1.5. So you may question, how can we produce 2.5? How can we produce 1.5? Actually, this one means average. So means sometime maybe 3, sometime maybe 2, you get an average, it will be 2.5. Okay, for reduced NAD. For reduced FAD, sometime 2, sometime 1. So therefore, average will be 1.5. Are you clear? So this is what it means here is in average. Okay, so if you calculate, so we have 10 reduced NAD, we have 2 reduced FAD, then you get the idea. Oxidative phosphorylations can help us to produce 28 ATP, 7-fold higher. Okay, or 7-fold, sorry, 7-fold, 7 times compared to the substrate link reactions. Okay, but the question here is, we haven't actually answered this. What is the role of the oxygen? Why without oxygen, pyruvates cannot enter? Okay, why why without oxygen, pyruvate cannot enter into the mitochondrial matrix? Why Krebs cycle and link reaction will stop? Okay, so this is a big question marks here, how the oxygen actually can cause this to happen. Okay, so let me explain now. Let us look at the role of O2. So generally, when we talk about the role of O2 in general, so they act as the final electron acceptor. Okay, or sometimes we can actually, some books also you say that they are the final electrons and proton acceptor. Now be careful. In our syllabus, you write final electron acceptor, correct. If you say final proton acceptor only, it's wrong. Protons must be together with electron because we do know that, okay, in the process, 4 hydrogen ions take 4 electrons, then you get 4 hydrogen atoms. So these 4 hydrogen atoms react with O2 or reduce the O2 to form 2 molecules of H2O. Correct now, guys, to form 2 molecules of H2O. Okay, but in this case, you can see that if you put in them all together, you can see that, okay, the overall equation will be 4 hydrogen plus 4 electrons, 4 hydrogen ions, but 4 electron plus O2, you get the 2 H2O. Clear not, guys? Okay, so what's the role of oxygens? Raw oxygens, they are final electrons and proton acceptor. Okay, so they accept the electrons and also the proton. Now, what's so important here? Now look at this. The reactions here. Okay, so I will show you guys 2 reactions. Okay, what is these 2 reactions? Number 1, reduce NAD. Okay, will become NAD plus hydrogen atom. So this process actually is oxidation. This process is oxidation. Why? Because you remove the hydrogen atom. When you remove the hydrogen atom, it's called oxidation. So therefore, NAD can be regenerated. Okay, so this oxidation process allows the regenerations of the NAD. So, okay, second process. Okay, so these 4 hydrogen ions plus 4 electrons and oxygens form water molecule. Okay, so in fact, we do know that these will combine to form hydrogen atom. So can you see that O2 accept hydrogen atom? Cannot. So when something accept hydrogen atom, so this is a reduction process. And we do know that redox always together. Okay, redox always together. So means that if we don't have O2, means that there is no reduction, means that no oxidations, NAD cannot be regenerated. This is very, very important idea. Clear or not? Okay, try to imagine, if no reduction process, because it's coupled, right? It's coupled together, right? I see that you want to donate your hydrogen atom, someone have to take the hydrogen atom. So if we don't have someone to take the hydrogen atom, you have to donate. You cannot release it, simply release and put the hydrogen atom in the matrix of the mitochondria. So means that we need to have the oxygen there. Okay, so now I understand the idea. So oxygen is why so important, because oxygen acts as the final electron acceptor. So if no oxygens there, means that reduction cannot take place, then you no need to reoxidize back your reduced NAD. So it means that NAD cannot be regenerated. And then your question will be, what's so important if you cannot regenerate the NAD? What's so important? This is very, very important. Okay, so what are so important about this NAD? Now look at this. Few things. What is the effect if we don't? Okay, what is the effects if we don't regenerate back the NAD? So first effect. Okay, so if we cannot, without oxygen, so this process cannot take place. Okay, reduce NAD, become NAD plus H. So this cannot take place. So means that you don't have hydrogen atom. So without hydrogen atom, you don't have this process also. So means that we don't have electron also. Can I see that? So if no electrons, means that electron transport chain stop functioning. Right? You don't have electron, What I need to carry? I can't carry anything. So electron transport chain stop. Clear? Okay. So if the electron transport chain stop, means that I can't create steep proton gradient. So if you can't create a steep proton gradient, what will happen next? No protons to move across the ion channel, right? So no energy is released, therefore oxidative phosphorylation stop. And concentrations of ATP now decreasing. Okay, that's one. Number two, pyruvates. You won't enter into the mitochondria now. Why? Because no ATP is an active transport. When now your ATP concentration is so low and dropped so low already, pyruvates say that's why I need to enter into the mitochondria. Correct or not? No ATP going to phosphorylate the pyruvate carrier, so therefore carrier cannot bring the pyruvates into the mitochondria. Okay, how about the existing pyruvate that already entered? So again, now look at this. Without the O2, ETC stop, no ATP, so means that reduced NAD will be accumulated. Correct or not? Because we cannot regenerate back the NAD, so means that the concentrations of NAD now is low until become no NAD. Are you clear? So if no NAD, you will look at the process, pyruvate to become acetyl-CoA. You need NAD. In the Krebs cycle, even worse, you need NAD. So now, because NAD cannot be regenerated, the concentration of NAD now keep on decreasing until no NAD. Therefore, what will happen? Pyruvates. Okay, sorry, these are link reactions and Krebs cycle stop also. So means that no point you send more pyruvate into the matrix. No point. Why? Because we don't have the NAD to oxidize the pyruvate anymore. We have no manpower already. So means that the concentration in this case, we say that without O2, okay, concentrations of NAD become a limiting factor. Okay, NAD concentration become limiting factor. Why? Because NAD cannot be generated. So this is how oxygen actually involved. So you can see that even though oxygen does not involve directly, you can see that the input, the needs of the oxygen in the link reaction, you can see the input of this oxygen in this Krebs cycle. But why? Okay, why? We say that without oxygen, pyruvates cannot enter into the mitochondria. Can you see that? Why Krebs cycle and link reaction actually stop? These are the explanations. Okay. So explain why in the absence of O2, pyruvate would not enter the link reactions and why Krebs cycle all stopped. Okay. So this is how we write. Okay. So oxygen acts as a final electron acceptor. It combines with the hydrogen ion and electron to form water molecule. So in fact, we do know that it's not really direct combine, but these two will combine into the hydrogen atom, then reduce the water. So we say that water, oxygen is reduced. So without oxygen, reduce NAD and reduce FAD cannot be reoxidized back to NAD and FAD respectively. So therefore, the electron transport chain now stop functioning. Proton gradient cannot be generated, hence no ATP can be synthesized. So why pyruvate cannot enter in the mitochondria to initiate the link reactions? Why? Because pyruvates, okay, I didn't put it here, because we do know that ATP is needed to transport pyruvate, okay, from cytoplasm into mitochondria matrix. Okay, and also no point, okay, move, okay, no point we move the pyruvate into. Why? Because without the NAD and FAD, link reactions cannot be initiated. Krebs cycle also cannot take place. Okay, and the reason is because NAD cannot be generated. Okay, or it cannot be regenerated. Okay, so means that pyruvate have to stay in the cytoplasm for anaerobic respiration pathway. So it depends on the yeast or depends on the mammalian cells. Are you clear? Okay. Okay, so now we do a quick summary on this ATP productions per glucose molecule. So we need to complete this table to summarize the number ATP, reduce NAD and reduce FAD obtained when one glucose is oxidized. Yeah. Okay, so we look at this. In glycolysis, how many ATP net gain? I will put net gain. So 2, okay, 2 ATP. But in fact, we do know that we produce 4 in glycolysis, but we use 2. We have to think. Okay, we need to. Okay, I say that minus out the cost, right? When we talk about the profit, reduce NAD, no, sorry, 2 molecule reduce NAD, reduce FAD, no, per glucose molecule. Link reactions, net gain ATP, no. Reduce NAD, yes. 2, reduce FAD, no. Krebs cycle, net gain of 2 ATP, or is a production of 2 ATP. Okay, reduce NAD, we have 6 of them. And then reduce FAD, 2 of them. So total out 4 ATP, 10 reduce NAD, and 2 reduce FAD. Get it correct? Okay. So look at the table 5.3. We're going to summarize the number of ATP, okay, that can be produced from reduced NAD and reduced FAD. So therefore, calculate the total number of ATP molecule that they are produced when one glucose molecule is oxidized. So reduced NAD number of molecule, we have 10 of them. Reduced FAD, we have 2 of them. ATP, we have 4 of them. Okay, ATP production in each molecule. So how many? So reduced NAD is 2.5. Reduced FAD, 1.5. This one, no, because it's already ATP. So total number ATP, you can see that 25 plus 3. So this is through what? Oxidative phosphorylation. Okay, and then how about ATP? Continue, you still have 4 ATP. This one is through substrate level or substrate link phosphorylations. Can you see that 28 plus 4 average 32? Okay, this 32 actually is average. Okay, per glucose molecule, when one glucose molecule is oxidized, okay, so we have the average of 32 ATP can be produced. Are you clear? Okay, now how we can calculate the 2.5? Basically, we base on the number of ATP that can be produced. Okay, so sometimes 3, sometimes 2 when we actually regenerate 1 NAD. So basically, we get an average of 2.5 because energy loss will be there. If you calculate the overall, so let me show you. So what is the max? If you calculate the energy release, okay, because you through and the process electron, okay, if an electron pass through, energy release, some of this energy will be released as a heat energy. So that is energy loss. You won't be able to get maximum. But if you calculate the energy, okay, you are assuming that there's no energy loss, maximum for reduced NAD. One reduced NAD can give us 3 ATP. The energy release here. Are you clear? Can use it to form 3 ATP. Reduce FAD. can use, okay, form 2 ATP. Are you clear? So we calculate, assuming there is no energy loss. Okay, assuming that no energy loss. So it means that if you times 10 of them, you get 30. You times 2 of them, you get 4. Okay, and then substrate level phosphorylation get 4. So total 38. So that's why in some books they use 38. 38 actually is a max. Are you clear? 38 is max. But in this 38, some books use 36. Why? Because they minus 2 ATP to transport pyruvate into mitochondria. Okay, matrix. So therefore, you can see that some books use 36. Okay, why is 36? Because they say maximum cannot be 38 because we still need to spend 2 to transport the pyruvate into the mitochondrial matrix. So total maximum is 36. But in our syllabus, we say 32. 32, why? Is average. So means that we already take into considerations of some of them we spend. Some of them we spend to bring the pyruvate in. Some of them we because of the energy loss. So average, I mean, we'll get 32. So why we can say 2.5 or 1.5? Because that is an average. Are you clear? Average. Okay. So that's all for the class. Again, you want to check the answer, you can check it here. Again, this is the answer for table 5.2. And also in table 5.3, right? The answer. Okay, so let's stop the recording.